I'm happy to introduce Dr. Yangkang Chen, who is a research assistant professor and lead of the machine learning and AI research at TexNet, the BEG, and the Jackson School of Geosciences. In 2015, Dr. Chen actually graduated from the Jackson School with his PhD in geophysics, so a good alum here from UTIG. But Chen is interested in computational methods that can be broadly applied to seismic signal analysis, seismic modeling and imaging, and earthquake monitoring. In the past decade, Chen's research has focused on applying AI techniques to various geoscience problems. So let's welcome Dr. Chen.
Oh, thank you for the introduction. First, before I start my presentation, I'll mention several things. First, I've been involved in a number of AI applications in geoscience, probably dozens of or even hundreds of applications. And this is the most amazing application for AI in geoscience I've ever seen. Because normally when you do AI, we often ask the question, why you need AI? Like sometimes it's just because like AI is hot and we need an application of it. And that also includes my own research. So most of the cases, it's just an application of AI, but not the real fundamental advances of AI in solving some problems that previously cannot solved by human. So this is really an example of how amazing the AI can be for geoscience. So I'll briefly introduce some of my collaborators along the road of this work. So this is, as we can see, this is a combination of work collaboration from different university, include different institutes, including students, postdoc, professor, and research scientists. Almost from around the world, different continents. This is the promotion figure you've seen from the email. Let me briefly introduce about these figures. So this figure shows our real-time application of AI in TexNet. So on the right-hand side, we can see error histograms, which show the errors distribution. The errors, the difference between our AI output and the manually checked magnitude. So as we can see, the magnitude are mostly around the zero magnitude difference, which means that for thousands of earthquakes, we have a very small magnitude error. And on the right-hand side, the bottom figure, we show a graph showing the econicity output magnitudes versus the preferred magnitudes. For a large number of these events, we have analyzed by our analysts. So we can focus on the red ones. We show that the econicity or the AI output magnitudes are actually almost the same as the final manually checked events. And here I also want to point out two dashed lines. This is the red dashed lines is the magnitude 1.9 threshold. Above this threshold, we manually check the events so that we won't miss any large magnitude. And the green dashed line corresponds to the magnitude 2 for the preferred magnitude. So in this figure is fascinating to me because it shows that the recall of magnitude above 2 earthquake is 100%, which means that for all magnitude above 2 earthquake, we do not lose anything. We do not lose any event, meaning the accuracy is 100%. So that's really amazing. So because of this very robust performance, we have applied in real time in TexNet. So the whole presentation is about to decipher the mystery inside this monitoring workflow. And this is outline of my talk. Firstly, I will introduce some background of this research because it's like years of research in the past decade, and I'll introduce briefly the architecture because this architecture part is really more mathematical and theoretical, and I think it's not the interest of most of you guys. And then I will show the applications. This is very important. Show the very robust generalization ability to different data sets from around the world, and also not limited to earthquake data, but also microseismic data. And also we apply it to two field data case studies in Midland and in Delaware, and then draw some conclusion. And this is the slide introducing the background of this research. Actually, we were among the first groups in the world to study AI in geoscience, specifically in earthquake monitoring. We started from the very basic like clustering methods in the beginning of 2016, and then we dive into more advanced architecture like a convolutional neural network or the transformer architectures. And one noteworthy work along the journey is the integrated earthquake detection and magnitude framework based on the vision transformer. So vision transformer at that time was the quite advanced architecture in the AI field. So we leverage this quite advanced AI technology to detect the earthquake. But the first piece of work is mostly for P-wave. So the P-wave is important for earthquake early warning study, because for earthquake early warning, we can only base on the P-wave to locate earthquake and then to provide an alert to public. We cannot use the S-wave information, because the S-wave information is the most destructive energy, right? So we only can base on the P-wave energy. So in this work, we designed a deep learning architecture to detect the P-wave, and based on the P-wave, we provide the magnitude, because the P-wave arrival time and the magnitude are the two critical information for providing a reliable location and then to issue a public alert, right? So this is the first noteworthy work along the journey. And then it comes to our latest EQCCD, which is short for earthquake detection based on compact convolutional transformer. So the compact convolutional transformer was also very advanced architectures when we designed this network. And we designed this network to detect not only P-wave, but also P-wave and S-wave, so that we can make a more comprehensive analysis about the seismicity, and then to create a more reliable and accurate catalog. And in this case, I want to briefly mention that we designed two models, one for the P-wave and one for S-wave, because if we know something about deep learning, we know that basically the training process is mostly a random process. So it's difficult to obtain the optimal performance for both P-wave and S-wave. So the more practical strategy is that we design two models for P-wave and S-wave to making sure that each model performs best for the P-wave or the S-wave, right? I'll skip this because it's not that important to the overall presentation. And from this slide, I will show some very fascinating results when applying this EQCCT P and S-wave picker to the real data. So this slide shows the application of this AI module to a public dataset, which is called STAT. STAT is short for Stanford Earthquake Dataset for AI, and it's the first benchmark AI dataset for earthquake monitoring study. And this slide shows the two earthquake events, which are all like large magnitude events. As we can see, both events are above magnitude 4, right? So for this large magnitude event, we do not make any mistake. Actually, predict our picket arrivals actually almost the same as the manually picket arrival. So that's no wonder, because it's large magnitude event. It ought to be accurate for any AI picker. And then we further applied to more challenging cases. In this case, we have like a smaller magnitude and with a lower signal to noise ratio. And in this case, as we can see, right, so several dashed lines correspond to either manually picket or either the AI picket. And we can see that even for these more challenging cases, our AI picked arrivals are still almost the same as the manually picked arrivals. So which still means that our AI model is robust for like more challenging cases. And then we further, test its robustness to even more challenging cases. So in this case, we apply it to very small magnitude events with very low signal flow ratio, and we can see the noise energy becomes much stronger in this case. But we can, by comparing the AI peaks with the manual peaks, we can still say that it did a pretty good job. So in this data set, we performs very successfully in this case. And then we show the errors distributions. And I also want to mention that in this case, we compare it with several other well-known or state-of-the-art pickers. Because when we do software or technology development, we need to compare it with the state-of-the-art, the best model in the literature. So in this case, we compared with the TexNet, the EQ transformer. Probably some of you know that. These two are the first couple of trials in leveraging the AI for earthquake monitoring. And I want to refer the TexNet as the first generation picker because it's based on a convolutional neural network, which is kind of the first generation deep learning architecture. And I want to refer the EQ transform as a second generation picker because it's based on more advanced transformer architecture. And I want to refer our EQCCT picker as a third generation. So it's kind of more advanced compared with the first and second generation pickers. And more importantly, it's a kind of actually a combination between the convolutional neural network and the transformer. Because if we know something about the deep learning, we know that convolutional neural network is good because of its efficiency, it's fast. And the transformer architecture is good at time series data processing, but it is slow. So our CCT architecture is kind of leverage the advantage of each architecture, so it achieves the best results without sacrificing the efficiency. And we can see from the error distribution, we see that the error of the latest third generation pickers is much smaller than the first and second generation picker. So this slide shows the error for data set. And more importantly, we want to see how generalize this model to different data sets, because it is also a common question we want to ask when we apply AI technologies. So this slide shows 4 different data sets. So first is a global data set, which I already mentioned is the standard data set. And the other 3 are actually from different areas of the world. So for Italy, for Japan, for Texas. So we apply this EQCCT module to vastly different geographical areas and obtain the quite good results for all of these data sets. So the first example is the Japanese data set. So in this case, we show 3 events, earthquake events. 2 of them are small magnitude events. One is the large magnitude event, magnitude 4. And for the first 2, obviously the noise is quite stronger than the third case. And but comparing the manual peaks, the manual peaks and the EQCCT peaks, we find that these dashed lines are almost overlapping each other, right? Meaning that the peaking error is very small. So this phenomenon is true for all these 3 cases, 3 events for the Japanese data set. And then we apply it to Texas data set. So as we can see, the first 2 cases, it seems that the noise is much stronger than the Japanese data set, mostly because our data set are acquired in the West Texas. West Texas is famous for like relentless oil and gas production and wastewater disposal. So yeah, there are a lot of industry operation there. So it's no wonder the noise is much stronger. But anyway, we found that the manual peaks, right? See the dashed lines, the comparison between the manual peak and the AI peaks are quite close, right? Even for this very challenging and noisy data set. And also for these large magnitude events, yeah, it performs very successfully because it's a necessity for AI for large magnitude event. We should make it very accurate for large magnitude event. And also this I show the example from Italy, right? For the Italy data set, and we obtain we can observe quite similar performance. And this slide shows the error distribution for the P-wave picking for three data sets, for the Japanese data set, Texas data set, and the Italy data set. And we compared it with the second generation picker, the EQ transformer. And we see that for the P-wave, seems that the errors from EQCCT is much smaller, obviously smaller, and the error histograms are more focused around 0, right? And we can also compare for the S-wave. And compared with the P-wave, we found that the S-wave error actually significantly higher because it's more, more scarcely, more diversely distributed, and also the difference between EQCCT and EQ transformer becomes smaller. Right? It makes sense because S-wave picking is more challenging than P-wave picking because there are some coda P-wave components in the seismograms which makes the S-wave picking more challenging. So it's a common sense for observational seismology. And this slide shows a very interesting application. Show that our picker is not limited to broadband seismic station. It can also be applied to microseismic data. So I want to clarify the main difference between earthquake data and microseismic data is that the sampling rate is dramatically different. For earthquake data, like normally we have 200 hertz or 100 hertz sampling rate, but for microseismic it can be up to 500 or 1000. So the sampling rate is quite different. So that's the reason why we want to test if this, this model trained from broadband station can be applied to the high sampling rate microseismic data. And in this case, it seems that from this slide I showed, it seems that it performs equally well. But I also want to mention that in this case, actually we don't have labels for microseismic data. Because remember, for earthquake data, we have analysts, government-funded analysts to pick the arrival. But for microseismic data, we don't have. We don't have the manually picked arrival, so we don't have the labels. But in this case, we use the best labels we have, which is actually not ground truth, which is based on semi-automatic picker. But we compared with the best labels we have and find that in some cases it performs equally well with the semi-automatic method, but for some cases we are better than semi-automatic pickers. It is also reasonable because it is deep learning based, while the semi-automatic picker is based on some combination between human knowledge and some early generation picker. So in this case, in general, we show that the EQCCT picker can also be applied to obtain quite good performance for microseismic data. And from this slide, I will show several real case studies in different geographical locations of Texas. For example, for this slide, we show the location results in Midland Basin. Right? So I also want to mention a little bit about this geographic location. So earthquake monitoring in Midland Basin is more challenging than in Delaware Basin because we have relatively smaller number of stations in Midland, and also we have a stronger noise level because there are residents in Midland Basin, and there are some part of it are urban areas. So we have challenging monitoring case for Midland Basin. And in this case, we applied not to the continuous data, we applied to the catalog data, which means that we extract waveforms from the existing catalog. and then we segment the waveform and apply the ecosystem picker to these segmented waveform just to verify the peaks in terms of the location. And in this case, we see that we apply it to like around 300 earthquakes in Midland Basin. And we found that for a majority of the locations, it is very accurate compared with the ground truth manually obtained the location. Only a few, like less than 5% or even fewer, we have like outliers. We have outlier location results, but it is still reasonable because we cannot let the AI picker to be 100% accurate. And we sometimes, in most of the cases, we can allow some errors. But in this case, the error is about like below 5%. We consider it acceptable. But for most of the other events, we obtain the exactly same location as compared with the more ground truth manually obtained location. Okay. And from this slide, I'll show an application of this ecosystem picker to continuous data. And we apply it to 1 month continuous data in the West Texas, more specifically Delaware Basin. We apply it to 21 stations, and we apply it to all the continuous data for each station. And then we do a complicated workflow, including association, location, relocation, and to create a high resolution catalog. So in this case, we show, first the geographical distribution of these stations, and we show the event distribution in terms of the magnitude and in terms of depth and in terms of the time period, right? And as we can see from this figure, we can see that we use ecosystem, we detect a lot more events compared with the catalog events. So in this case, we detect more than 11,000 events, mostly very small earthquakes, compared with the TexNet catalog on the website, 250 events. And in this figure, we show the depth distribution, and we see that there are some like abnormal depths from this ecosystem catalog. They might be wrong location. We need to further check it, but in general, for most of this part, we consider it as reasonable locations. And also for this daily distribution of the seismicity, and we found that traditionally, because of the capability of analyzing the seismic data, we can locate like 7 events per day, mostly above magnitude 2. But with the AI picker, we can locate more than 300 or even more, 400 earthquakes per day. So that's a dramatic change. And this slide shows the earthquake density plot for all these detected events, 11,000 events within a month period. And it's difficult to plot all these events completely, because that will, it's difficult to analyze the details in the data. It's just because the data is so huge. But instead, we plot the density, earthquake density on this, and this density map is overlaid by different periods of the earthquake events extracted from the catalog for 1 month, and for 3 months, and for 6 months, and for 1 year. And we found that even for 1 year, we only detect like 2,000, a little more than 2,000 events from the website version of TexNet catalog. And by 1 month, we detect actually more than 1 year's detectability from TexNet. So that's really amazing, showing that we can detect much more events using the AI. And this slide shows the relocation. So relocation of these events. So I want to mention a little bit about the relocation. So normally the first step of earthquake monitoring is, of course, the picking of the P wave and S wave, and then we use association procedure to associate all those peaks to certain events, and then we do location. And then those locations are rough location. To obtain more accurate high resolution catalog, we all do relocation, and the relocation is kind of last step of the whole earthquake monitoring step to output a really high resolution catalog, as shown in this figure. And this high resolution catalog really delineates some faults structures about this area. So in this slide, we show the relocation results between the TexNet catalog and the EcoCCT catalog. So on the left-hand side, we show the comparison before and after relocation, right? Before relocation, we have like around 211 events on the catalog. And after relocation, we decrease a certain number of events and we retain about 166 events. As we can see, because of the very short period of monitoring, we cannot delineate really detailed structure in this area. But when we look at the right hand side using the AI picker, we are using only 1 month's data. We can delineate these structures, these fault structure very clearly, beautifully, right? After relocation. And this slide show a typical example of one event detected by TexNet and also by the EcoCCT, the AI picker, right? And in this case, this event is detected by both, right? Both methods, manually or the AI module. And this magnitude is like 1.2 magnitude events. What's mentioning is that for the traditionally we analyze it manually. We detected from 7 stations without use of the AI picker. But with the AI picker, we can detect it from more stations. We detect it from 15 stations in this case, which actually we expand the database about the peaks, and then based on the more peaks, we can hopefully get a more accurate location. And in this case, actually the depth difference is quite obvious. In this case, for example, the EcoCCT location is about 2 kilometers deeper than the TexNet regional catalog. In this case, because we know that we have more stations and we have more peaks, for this case, probably we think that the EcoCCT location is more accurate, but we don't know. We have to do further study to verify this. And this slide shows a very interesting example about a very small earthquake. In this case, the magnitude is only 0.4. And in this case, this event is lost by the TexNet catalog, but picked it out by the AI method. So, and in this case, we plot the waveforms according to the epicenter distance. We see a beautifully aligned P wave arrival and the S wave arrival. So from these beautifully aligned arrivals, according to the epicenter distance, we kind of can manually verify this is a real event. This is a high quality event detected by the AI, right? Which was missed previously by human. And this slide shows the interesting sensitivity analysis about the density, the station density. A common question is that what if we don't have a dense network, like back to 3 years ago or even 6 years ago? How capable we can detect these events? So, we decreased the number of stations from 21 stations, which is up to date, to 12 stations like 3 years ago, and to even 8 stations like 6 years ago. So we can we want to see how many events we can detect, right, in each case. So as we can see, from like cutting off the half stations, we can still detect 7,000 events. But by cutting off more stations, we cannot detect as many events. We detect much fewer events. In this case, 5,000 events, right? So it indicates 2 things. First, the earthquake density matters, right? The more, the better, of course. And secondly, even with a very few number of stations, we can still detect quite a large number of events. So that indicates the capability of the AI picker, right? And on the right hand side, we show the event distributions. As we can see that for the large magnitude events, actually all these three cases are pretty much the same. They differ only in this part, right? So the small magnitude part, we detect really a large number of ultra small earthquakes. And this slide shows the p-value comparison. So I also want to mention a little bit about the p-value. So p-value is a metric to indicate the potentially the causal factor of this earthquake, either human-generated anthropogenic injection induced earthquakes or tectonic-related earthquakes. Normally, we think that a smaller p-value, like equal to 1, correspond to more the tectonic generated events, with higher p-value indicating the anthropogenic injection caused seismicity. And in this case, we compare the p-value for three cases. The first case is for like the AI catalog for 3 months, and we have a p-value, of course. And we also compared with the two other cases. One is the TexNet catalog in the same period, the 3 months TexNet, and then also the TexNet catalog for the whole period, 7 years. And we found that the p-value from 3 months is monitoring using AI is much closer to the background value, p-value, which is from the whole TexNet catalog. And traditionally using 1 month's data in the TexNet catalog, we have a much deviated or wrongly predicted p-values. And in this case, we conclude that using a very small period of monitoring time, we can kind of get a pretty reliable p-value estimation, right? And also, this slide shows a GitHub repository of our Ecosystem Picker. We provide the model, and we provide some example scripts so that anyone can play with the model. And we have provided a demo dataset, which is from Japan. And of course, we can put our text data on this repository, but it's quite straightforward. So anyway, in any case, we promote the open science environment for developing such a tool. And finally, some conclusion. I want to note that this is not the last slide. I have 2 more slides. I just want to give you more insights about this track of research. In general, we found that the AI picker, right, performs better than the state of the art. So it is a scientific advance in this field. And also it obtains a quite good statistics on benchmark data in terms of different statistical measures, standard deviation, or the error, mean absolute errors, etc. And it is highly generable. As I show, it is applicable to vastly different data sets from around the world. And it also helps us to obtain the very similar locations because of their very accurate arrival times picking performance. And also it helps detect many more unknown small events, right? As we can see, most of the newly detected events are small and ultra small events. And it seems that like if normally, right, we do an application work of such type of advanced technology, and then it's kind of over. And but we really don't enjoy the most advantage from this technology. So what we can do next? Actually, we have already done some on this. So and if you are familiar with deep learning, we know that the deep learning is a data-hungry science, and we need data set, right? And the reason why the earthquake field it can achieve such amazing breakthrough in terms of AI is that because earthquake data are mostly open, right? And we don't have any issues about the privacy, about the data privilege. And we can leverage all the available data from around the world. So then we can develop really advanced technology that can, better deal with this data. Like it's like some success lessons we learned from the computer vision side, which really, make the AI development popular in all natural science fields. And to foster a more in-depth study in this track, we have compiled a data set using all the peaks, the manually peak day and night hard work from TexNet analysts. We compiled data set, large scale data set, more than 76 gigabytes in HDF5 formats. And then we pretty much include everything, key information in this data set, including P-wave, S-wave arrival information, location information, station information, and we also include the causal factors based on our previous studies using some physics-based causal factor analysis approaches. So we also include these causal factors in this data set. Hopefully we can, we can let people use advanced technology to classify those seismic data into different causal factors. Yeah. And we can also, because of the data set, this data set specifically designed compiled data set in Texas, we can apply transfer learning. Right? We can first build a model, globally applicable model using a large data set from around the globe, and then we can fine tune the model using this specifically designed local data set to further improve the performance of this approach in our Texas data set. So this slide shows the very good examples on how the transfer learning can be in terms of the peaking accuracy. So on the left-hand side, we show the P-wave and S-wave peaks error distributions before applying transfer learning. And on the right-hand side, we show the error distribution after transfer learning using the Texas AI dataset I just mentioned in the last slide. And we can see a dramatic improvement, right, in terms of error from left to right. And on the right-hand side, we show a typical example for one event, which is around the magnitude 1.3. And traditionally, we can use EQCCT to detect this event with 10 peaks, as I mentioned in the previous slides. And using the transfer learning model, we can detect even more peaks from very noisy data. So in this case, I highlight the newly triggered stations in these magenta colors. So when we view all these stations on the map, we can see that. So traditionally, no, not traditionally, actually using the early version of the QCCT method, we can detect it from nearby station, right? Like these the blue stations. And using the fine-tuned model, we can detect it from far away stations indicated by these magenta stations. So which is really amazing, showing that by transfer learning, we can even push the limit of the detectability. Right? And the last slide is what you have seen, this real-time monitoring slide. So this is the best slide I like because it really shows that we already apply this AI technology to real-time in production. So yeah, that's my presentation. So I'm glad to take any questions, comments.
So for the very small, actually small earthquake, and something, magnitude smaller than 1, and as you said, there is even no ground truth,
yes,
and there's no label.
Yes.
How do you evaluate your result?
Yeah, it's a good question.
Is there any other evidence to help you to evaluate that?
It's a good question. So on the one hand, we can use some quantitative metric already developed in the earthquake location field, like the residual arrival times, like calculated from the observed peak arrival time and the normally calculated event based on the location. So this metric is included in like normal mainstream location software. And we can use that IMS, like a residual mean error metric, to quantitatively measure the quality of this location procedure. Yeah, so that is one hand, and another hand is so we can view, right? We can manually view the peaking performance in according to the epicenter distance. We can see beautifully aligned the P wave and S waves, right? And we can also see the location on the map, and we can use like a nearby events. We can use a large number of events in terms of their alignment around the faults, right? And we can also verify if this is a high quality or reliable location. So it is a very important aspect for verifying this result. So we generally have these two ways.
And the second question about there is one TexNet, I mean, it's in one slide you show there is one event that is missed by the TexNet. And but I mean, it seems the signal ratio is pretty, it's at least it's fine. But what's the reason for?
Good point. Yeah. So it refers to the difference between single station location or monitoring and the multi-station location and monitoring. So basically, when using single station, we can detect way more events than multi-station monitoring, because for multi-station monitoring we have to, we have the requirement that this event is detected by multiple stations, right? And but for the single station, it can be can be very small event near the station, and we can for very small earthquake we can use single station detected easily, but these very small earthquakes may not trigger like far away station, so that causes a issue when doing association. The association is to associate all those peaks from different stations into certain events. So when we do association, we will remove a lot of peaks. So that means that answers your question that for some stations, the signal ratio seems quite good, but we still lost it in the associated event, because we have constraint that we needed to detect it from many stations.
Yangkang, let me add a few things. Can you go back to slide 18? First of all, I don't think I know all of you. I know a few of you. So my name is Alexandros Sabaidis. I joined UT back in 2016. I designed and developed TexNet. So I'm the leading seismologist of the group. And I recruited Yangkang a couple of years ago. And he brought with himself all these AI approaches that we're all keen on. Let me explain a few things. I would like to come up with this slide first. So the upper right corner, you see the Gutenberg Richter actually, which you see the number of earthquakes per magnitude. And there is with two different colors, Yangkang is presenting the catalog earthquakes and the EQCCT. We need to update this figure of Yangkang. Then what you miss here is because the catalog here is only the public events that the analyst has posted to the website. It doesn't have all the events that have been detected by the system. And when I'm talking the system, the traditional approach we use, which most of the network use, is the STA-LTA. So the approach we use for detecting the earthquake. So all the detected events are not in this figure. And we name them as reported events. So reported events are the earthquakes that we detect, but we don't publish all of them. There is a threshold defined by the group with what goes to the public. And of course, if anyone that would like to look at the reported events can get access from us. If you send us an email, we can give you that. So the big difference with the QCCT is that we actually manage to decrease the margin of completeness. So this figure shows that the margin of completeness with the QCT is like 0.9, which usually with the reported events is close to 1.5, 1.4. So we go to 0.5 magnitude scale lower values, which is good because then we see the migration of seismicity. We can see a lot of things with lower magnitude earthquakes. Now, if you go to your figure, the last figure. So the reported events is what you see there with the blue. So you see there that the small earthquakes are already detected. But as I said earlier, not all of them, maybe not the same quality, because we don't have so many peaks. So the system is using an approach where marks each peak with a value, so that you can use those peaks with a weighting factor in order to calculate, to associate the peaks to create an event, and then locate the earthquake. And when it does this, it actually what it's doing is moving out or in different peaks to finally do the location, and using a voting factor to decide if this is an earthquake or not. So the system has an approach already set it up. So what we have added to the system, to the earthquake management system, is that we say, okay, get peaks not only from STA, LTA, but get peaks also from QCCT, and then associate them. So now the system has more than double the number of peaks that it is used to associate them and create the event. So we have more events that are, as Yangkang said, of lower magnitude. What you asked at the beginning, your first question, Yangkang, we can use the reported events that are manually reviewed by the analysts for smaller magnitudes for the few, let's say, peaks that we have already in our system that are manually reviewed. And this can be used for checking with AI if EQCCT provides good results for the peaks, because actually that's what it's changing. You cannot ask an analyst to give you a peak when he doesn't see something, but at least he or she can see something in the close by stations. So if QCCT for small magnitude events fits with the manually reviewed peaks for the nearby stations, that's a success story. I hope they replied to your question.
Thank you.
Can you flip back to slide 18 again? So on your panel B, I can see that you have like a missing magnitude 3, some missing magnitude 3 events. Is that just because of the reported versus
I don't know exactly, I don't know, yeah, it might be the report, but usually we publish 3 and above.
Okay,
So there shouldn't be, yeah, that's a good point. We have to check which event is missing there.
because I just thought magnitude 3 was a bit of a big
Yes,
event.
yes, it's a big event.
Catalog.
Certainly.
And then, I'm sorry, I'm gonna be a pain. Can you flip back to your last slide again? I know. So in this panel B again, these blue dots, you have a preferred magnitude and then the EQCC magnitude. And actually you seem to have kind of like a horizontal trend around magnitude 0. So why is it that you're getting like a fixed magnitude from EQCC for a whole range of preferred magnitude? Why is it kind of like preferentially choosing to put these small magnitude earthquakes at a magnitude 0, pulling it away from kind of the linear trend that we expect?
Very good point. I think it's possibly because the different velocity model we use when we do a secondary location based on the EQCCT catalog, the very initial real-time catalog. So the different velocity model will cause the consistent shift on the depth and the magnitude. So that explains why we have like a trend, because we use a more accurate velocity model in the secondary location, and then that will consistently lower or increase the magnitude.
Okay, thank you.
So that's the only difference we apply for the preferred magnitude.
Yeah, thanks for this talk. It's really cool. I have 2 questions. The first one's maybe more of a comment. For your kind of evaluation of performance on different data sets, I'm like pretty amazed at like the generalizability of this picker. You didn't have to do any tweaking or retraining of the model? It's just straight applying it to, yeah, I don't do this kind of stuff, so I might be wrong, but my understanding is that's pretty rare. Like, not a lot of pickers are able to do that. It's, a lot of these, to my understanding, these machine learning models, they work kind of on the data.
It's probably because, the testing data set are at least very famous data set from Italy, from Japan, and from Texas. These data set those data are like well studied in the literature. And in the global data set, although we don't include all these regional data set, but we include some representation of this regional data so that we kind of have some generalization ability there. But for very rare, remote or very unknown areas, data is probably a problem. Yeah, I can.
But I guess as much a question as the comment, that's really interesting. That's great. And then my other one, you don't have to flip back to it, but in that multi-panel plot we're looking at, there's a lot of distribution across depth, including down to like 20 kilometers or something, right? So I'm just curious if you could comment on, you mentioned very briefly that, okay, maybe some of these depths need to be investigated a little bit more, but could you comment on if you think EQCCT is actually picking these really tiny events, or if...
Also a very good point. So the figure is based on very initial real-time catalog using a very globally average velocity model, which basically a constant in the shallow part. So, and then if we do the secondary location, we will adjust the depths a little bit so that we can have more reasonable depths, but we can still, as I said, there are always outliers.
Sure.
And that outlier can be like 5% around also 5% outliers. So for those outliers, we have unreasonable depths or unreasonable magnitude. That's for sure. Yeah, we cannot completely remove that.
Thanks.
So you said that the p-value for NG seismicity is typically greater than 1. So what would be like a reasonable number? And if the number you got?
Induced seismicity is normally higher than 1. Like if it is strictly 1, that means tectonic earthquake. So it depends on some physics inside the p-value calculation, because it's a long used metric to study the general cause of this of the seismicity. And I can give you one example, like for hydraulic fracturing induced earthquakes, it normally has like a p-value close to 2.
Okay.
And that's quite reasonable, because for hydraulic fracturing, it injects very high pressure instant fluid into the formation, and then it very quickly generate the seismicity. And in that case, the energy release rate is very, very high, and it makes there are so many like small earthquakes happening instantly. So in that case, it's around 2. And in our case, most earthquakes are like long-term cause, mostly from the wastewater disposal. So it has a long-term effect on the formation of the bigger areas. So it is closer to a tectonic earthquake, but it is still like larger than 1.
Okay.
Regarding this, we published a paper back, I think it was 2019, that we showed that the spatial temporal seismic distribution of hydraulic fracturing in seismicity is very prompt in space and time, and that gets more like a clustering seismicity distribution, which we don't see on the saltwater disposal, but follows more or less some distribution that you cannot distinguish easily between the natural tectonic and the natural saltwater disposal. I want to add something to your question about this magnitude thing. So first of all, Yangkang, I think you use the S91 model.
Yeah, the initial version.
Yeah. Okay, so the TexNet catalog use a local Earth model. So the Earth model is different. And when we calculate the magnitude, we use the hypocentral distance, not the epicentral. In that case, the depth has an effect, especially if you are close to the source. So this is one thing, and the other thing you have to keep in mind is that Yangkang, in one of it's on his slides here, he said that the sigma on the mean value is plus minus 0.33. The analyst is sig by 0.2.
Okay.
So there is a difference in the standard deviation already between the magnitude calculation. So that might affect it. There is a trend, as you mentioned, but we have to think how we can explain that. Maybe there is an effect of the using more stations, because one the model more stations doesn't fit very well. So that's why.
Any final questions? Anyone online? Well, this was a great discussion. Let's thank Dr. Chen one more time. Join us next week, Wednesday, for Pancake Day.
So